started Unit 5. We did 5.1 and 5.2. That was the ratios and proportions, and then scale factor and similar figures. So we did those notes on Thursday. You should have those. And then that Friday before Thanksgiving break, y'all just had a work day. This was one assignment. It says 5.1 and 5.2. It was not two separate assignments. It was one combo assignment. Okay, so what we're going to do today, we're going to keep moving forward in Unit 5. If you have forgotten some of this stuff, you may want to go back and do some more of this practice. If you finished, it will let you do more practice. If you have not finished, obviously you're going to need to go back and do that, and you can review those notes. Okay, but we're going to continue in Unit 5. We're talking about geometric mean today. And it builds off of proportions, because we use proportions to find geometric mean. So here should be on the front side of the notes there that have the title. If we have time to look at the back, we will. If we don't, it's not a big deal, because this is just an alternate way to look at geometric mean. And I think the great majority of y'all will prefer the way that we do it on the front. So we'll just see if we have time to do the back or not. It's no big deal if we don't. But what geometric mean is, okay, is a value. If you have in the proportion, A is to X as X is to B. Remember, a proportion is setting two ratios equal. So if you have a proportion where the denominator of one side is the numerator of the other, then that value, they're the same. That X is the geometric mean of A and B, of these other two values. Okay, so we're going to start by just being given two numbers and asked to find the geometric mean. So I'm just going to set up this proportion. They're telling us if this is your A and B, find the geometric mean. So we're looking for X. So we would set it up. We would say, okay, 4 is to X as X is to 9. And we simply set up the proportion. Now, who remembers when we have a proportion set up, before the break, we only had one missing piece of our proportion. You had 3 of these were known and 1 was unknown. What was the method we used to solve when we had a proportion set up? Cross multiply. Does that sound familiar? So cross multiplies when we multiply the values that are diagonal from each other in the proportion, like this. Some of you may have called that the butterfly method, if you were taught to call it that. But this is cross multiply, is how you solve a proportion. So remember, when we cross multiply, we're multiplying X times X. Well, when you multiply something by itself, isn't that squaring it? That's what that's when you have a variable times itself, you can write that variable. I'm going to write X times X first to help you see what's happening. And then I'm doing 4 times 9 on the other side. But when you have a variable times itself, when you have X times X, that's X squared. Okay, and then 4 times 9 is 36. So some of y'all are going to go straight to that line. You're not going to write this one, X times X equals 4 times 9. You're going to do that in your head when you're cross multiplying. You're going to say, okay, X times X is X squared. 4 times 9 is 36. And you'll just write this line, and that's fine. Okay, now we need to think back when we are solving in algebra, when you're solving for your variable. You do the opposite operation to move things to the other side of the equation. The opposite of adding is subtracting. The opposite of multiplying is dividing. Who remembers what the opposite of squaring something is? Say it again. Do what you did again? Yes. Okay, so Evelyn's making the symbol for a radical. Okay, it looks like this. Does that look familiar? Anybody remember what that's called? Square root. Square root, good. So the opposite of squaring something is taking the square root of it. Okay, so a square and a square root, when we do that, those are going to cancel each other out here, and I'm just going to be left with the x, which is what the goal was. That was the point of taking the square root. Okay, so on the left side here, I get just x. But over here, I need to take the square root of 36. If you don't remember what a square root is, what tool do you have at your disposal that you can use? Desmos, calculator. Just go type this in, square root of 36. If you do remember what a square root is, you're asking for the value that multiplies by itself to give you this number. What times itself equals 36? Does anybody know? 6. 6 times 6 is 36, right? So 6 squared. So the square root of 36 is 6. And again, if you don't know that, you have Desmos that you get to use. You don't have to be able to do that in your head. It's good to know your perfect squares. 1 times 1 is 1. 2 times 2 is 4. 2 times 3 is 9. And then 4 times 4 is 16, 25, 36, 49. You can have a list, if it's helpful to you, of perfect squares. If you can't do that by hand or in your head, again, it's fine. Just type it in the calculator and it will tell you the square root of 36 is 6. Okay, when you're in Desmos, if you don't remember, I'll show you where the square root symbol is. So you get your keyboard here. It's right here. Okay, so you would type in the square root of 36 and it tells you it's 6. Okay, so just use Desmos if you don't know your square roots. Now, you'll only know the square roots in your head if you know perfect squares. A lot of times you're going to have a decimal and we're going to have to make sure we remember how to round. So for B, I'm going to go a little bit quicker here. I'm looking for the geometric mean of 6 and 15. So 6 is to x as x is to 15. So when I cross multiply, that's going to be x squared equals, and then 6 times 15, and that's going to give me 90. So I've got x squared equals 90. 90 is not a perfect square. So when I go to take the square root this time, I don't get an integer, a whole number. I'm going to get a decimal. So what I want you to do when you go in here and you do the square root of 90, I want you to round to the 10th place. That's the first number after the decimal. Okay, when whatever, you know what place value you're rounding to, you always look to the right of that. And if it's 5 or higher, you round this number up, right? So since I want to round to the 10ths, right now that's a 4, but I look to the right and there's an 8. So should I leave that as a 4 or round it up to a 5? Round it up to a 5. So I'm going to say approximately 9.5. Okay, last one like this. 5 is to x as x is to 20. This is how we find geometric mean. Some of you are going to do this. Instead of writing it here in part A, I did it like in 3 lines. Okay, here I did a line and then I took the square root. Some of you may jump straight to this and say, okay, it's going to be the square root of that product, 5 times 20. So if you want to jump straight to that, if you want to jump straight to x is the square root of a times b, you could jump straight to that. What's 5 times 20? 100. And this 100 is a perfect square. The square root of 100, what times itself equals 100? 10. Type it in Desmos if you don't know that. Okay, so you can go straight to this step. If you don't like setting up the proportion and solving, you can just say, okay, x is the square root of that product. So you can just do 5 times 20, take the square root, boom, done. Make sense? All right, now we're going to apply it to triangles because we've been dealing with triangles in this unit. We're going to keep dealing with triangles. When you have a right triangle, what's a right triangle? How do you have a right triangle? A 90-degree angle. So if you have a right triangle, that means you have a 90-degree angle. Triangle ABC, here's my 90-degree angle at angle C, right? So I've got this big right triangle ABC. Do y'all see that? That's the outer triangle, the large triangle. Going to kind of color code here. If you want to color code with me, you can. When you draw the altitude, remember the altitude is the height of the triangle. Ooh, that is a little thick. The altitude is the height of the triangle drawn from a vertex to the opposite side. So this says when you have the altitude to the hypotenuse, that means it's got to come from the right angle to the hypotenuse, because the hypotenuse is the opposite side of the right angle. So if you need to label, there's your right angle, here's your hypotenuse. When you connect that line, that's your altitude. Okay. You have now created two smaller right triangles. Do you see that? Because an altitude is perpendicular to that side. So it makes this 90-degree angle. So both of these angles here at this intersection are 90 degrees. So you've got this small little right triangle. You've got this medium right triangle. And then you've got the original large right triangle. Okay, so I'm going to color code those. So the small right triangle is CBD. So the small one in here. Okay, that's your small right triangle. Then you've got your medium CDA. Okay, so or ACD, doesn't matter which order you name it in. Okay, so we've created these two small right triangles by drawing the altitude of the original large right triangle here. Okay, so is everybody visualizing the three triangles? We have the big original one and then the two smaller ones created. Yes? Those are all similar to each other. We talked about similarity before the break. We said if the images are similar, if you have similar polygons, in this case triangles, they are proportional side lengths. Okay? So the long side, the long leg of one is going to be proportional to the long leg of the other. The hypotenuse of one will be proportional to the hypotenuse of another, right? That's what similar figures mean. They mean they have proportional sides. So we're going to be able to set up proportions. Does that make sense? So far, so good? All right, so let's look at this triangle, and we have a table to organize all of these different measurements. Because I'm going to color code again. We have the outer big triangle, the original triangle here. And then it's broken up and you get this small triangle in here. So the small triangle, the large triangle, and then you have that other medium-sized triangle. Got it color-coded so you can see what we're referring to. Now, in those three triangles, let's look at the small one first. In this small triangle, here's the right angle. So the hypotenuse is the y. HYP, that's hypotenuse, that's y. Okay. Now, these are the legs. The 6 and the x are the legs. Those are the sides that meet at the right angle. The x is shorter than that 6, isn't it? So x is the short leg, 6 is the long leg, and y is the hypotenuse. So that's where that came from. In the medium triangle, here's my right angle. So across from it is Z. So Z is the hypotenuse here. Okay, the legs are the 6 and the 12. 6 is less than 12. So 6 is the short leg, 12 is the long leg. And then the original big outer triangle there, the green, here's your 90-degree angle. So across from it, here's my hypotenuse. I don't know that total length, but I know it's the 12 and the x together, isn't it? So that's why it says 12 plus x, because that's this whole thing, this whole side. And then the legs are the y and the z. And we can see that the y is shorter than the z. Okay, so y is the short leg and z is the long leg. Are we okay with where these values of the table came from? Okay, this table just helps you visualize what your ratios should be. You can set up any ratio, short to long, long to hypotenuse, short to hypotenuse. It doesn't matter. However you want to do it to set up a proportion between any of the three triangles. You can pick any two. Now, I'm going to start with this one because I see right away this proportion has one missing piece, x. So when I set up this proportion, I'm setting up x is to 6 as 6 is to 12. If you need to put in words what you're doing the short leg to the long leg. That's the ratio we're looking at, short to long, in the small triangle and the medium triangle. Is everybody good with how I set this up? These have to be proportional. That's what that theorem tells us. So if they're proportional, I can just cross multiply and find x. So when I cross multiply here, I get 6 times 6 is 36. And 12 times x would just be 12x. If I'm trying to solve for x, how would I get rid of that 12? I would divide it out. It's 12 times x. The opposite of times is divide. So I get x is 3. So that means that this little piece here is 3. So I'm going to put x is 3. And I'm going to put that in my picture. That's a 3. So now do I know that total length of that green hypotenuse? What's 12 plus 3? 15. So I can come and put that in my table. Since that's a 3, now I know that's 15. So far, so good? So I found one of my missing pieces was 3. Now I'm going to look for another proportion that I could set up. So let's use, here I see the geometric mean where it's the same in the denominator and numerator. I see it right here. Look at this proportion. You'll see it. 12 is to z as z is to 15. This time I'm setting up long leg to hypotenuse. If you need to put it in words, it's long leg to hypotenuse. That's the proportion I'm setting up. You don't have to label that, but for your notes, if you want to, you can. So this time I'm going to end up with that z squared because it's the same variable. And I know that that's okay. I can do that. And 12 times 15 is 180. Now, what did we say? What do we do to get rid of the square? We take the square roots. So I'm finding the geometric mean between 12 and 15 here for this one. So then that comes out to a decimal. And I'm going to round it. So I'm going to say, okay, the square root of 180. And I want to round to the tenths. So should I leave it a 4 or round it up to a 5? Leave it a 4 because that's a 1. The 1's not going to round it up. So it's going to stay 13.4. Okay, so I've got my X and I've got my Z. So the only thing left here to find is the Y. Now, I could do a ratio. I could come over here and I could do something like this. And I could look here and set up this. Oops, that was supposed to be a different color. Green. I could set up this ratio because now I know Z, don't I? Okay. Or I could set up here like this because now I know Z. But Z is a rounded decimal. So I would prefer that we don't use the rounded values because they're not going to be exact correct answers. So I'd rather look at something not as obvious. When you look here, look for that geometric mean. Where do you see Y twice and then you know the other number? So I could do, now that I know that that's a 3 and that's a whole number, I could do short to hypotenuse. So if I set up the ratio of short to hypotenuse, that would be 3 is to Y as, and then the short to hypotenuse. Y is to 15. And then I don't have to worry about using a decimal that I've rounded. So I would do my Y times Y is Y squared. Okay, my 15 times 3, 45. And then I would take the square root. And this is another one that I'm going to have to round. If you do square root of 45, we're going to round it. It's going to be approximately 6.7. Now, if you wanted to check yourself, label this in your picture. So we got 6.7 here. We got 13.4 here. All right, y'all have a good lunch. I'm going to finish up this problem for the video I'm recording, and we'll finish with y'all when we come back. Okay, but what's happening here, what I was saying is, if you want to check your answer, you know that in right triangles, you learned a long time ago that Pythagorean theorem, a squared plus b squared equals c squared, is true for all right triangles. So you can use this to check. So the AB are the legs, C is the hypotenuse. The C is what we said was 15. And then the legs were 13.4 and 6.7. So I could check this in Desmos. And so I could come over here and I could write 13.4 squared plus 6.7 squared. And then on another line, I could write the 15 squared. And you see how those come out not exactly the same, but that's because we rounded these decimals. We didn't use the exact value, but it's pretty darn close. Okay, so you can confirm, okay, those legs squared add up to equal the hypotenuse squared. Okay, so that's just an option for checking your work if you want to check your work. Okay, so again, that part there is optional. Okay, check with Pythagorean theorem. Okay, I'm going to do one more like this. So we have to label and fill out our table. So I'm going to color code again my small triangle. Let's create my small right triangle, my medium right triangle, and the original large right triangle. So here's the original outer one. Now this one is harder to see for some people, like which sides are larger or smaller. So reference what we did up here, maybe, if that helps you. Well, I guess we didn't label it. Okay, so reference this first example. When you drew your altitude, okay, the smaller side that the hypotenuse split into here, in this case, it was a 3 to a 12, so it was much more obvious that this was smaller. Okay, so that's going to be the smaller triangle. Okay, the one that you split into the smaller portion. And that is going to be the short side of the small triangle. So here, when I split this 5 and 7, 5 is smaller than 7. 5 is less than 7. So that means that this is the smaller triangle. Oops. And that the 5, I'll write that in, and that the 5 is the leg. Okay, again, reference this up here. Okay, that smaller side, that was the shorter leg of the small triangle. So 5 and X look pretty close. It's hard to tell, but just know that that's always going to be the shorter side. So the shorter side, the shorter leg is the 5. The longer leg is unknown, X. And then the hypotenuse created, there's the right angle. The hypotenuse is the Y. Then in the medium triangle over here, the longer piece, the 7 was longer than the 5, right? So this is the larger than the yellow triangle. Okay, look over here again. When you create that longer side of the hypotenuse, that's the long leg of the right triangle. So even though the X and the 7, again, maybe you can't tell by the way it's drawn, the 7 is the longer leg. So the 7 is the long leg, the X is the short leg, and then here across from the 90 is the Z, is the hypotenuse. And then in the large triangle, that's the green one, okay, the hypotenuse, the total here is 12. That's across from the 90. So the hypotenuse is 12. Okay, and then again, you need to determine which is the long leg and which is the short leg. Look at how the hypotenuse was portioned out. This side, the 5 is less, so Y is shorter, okay, than the Z, because the Z is on the longer side of the portioned hypotenuse. So Z is the long leg. Not gonna work again. There we go. And Y is the short leg. So once you have your table with that organized, you can again see proportions that you can set up and solve. Okay, so I'm going to do 5 is to X as X is to 7. And that's a geometric mean. You've got X squared equals 35. You take the square root. 35 is not a perfect square, so we're going to end up rounding this one. And we're just rounding to tenths, unless you're told otherwise. So the square root of 35 is approximately 5.9. That here, approximately 5.9. Now I'm going to look for another proportion. I see one with the z's as the geometric mean of 7 and 12. So I can set up 7 is to z as z is to 12. So I again do my cross multiply, find the geometric mean here, z. So I end up with z squared equals 7 times 12, which is 84. Another non-perfect square. So when I take the square root, I'm going to round, and that one's going to round to approximately 9.2. Again, I've got decimals here, and I don't want to use those in any of my proportions to solve for another piece, because when you use a rounded value, to find something, your answer is going to be slightly off. So again, I'm going to look for non-rounded values. So same concept, I'm going to do the x is to y as y is to 12, like I did in the previous example. So 5 is to y as y is to 12. Y squared equals 5 times 12, which is 60. And again, 60 is not a perfect square. So I end up having to round. And that comes out to approximately 7.7. Now again, I could come in to Desmos and I could verify and just double check that I've done this correctly by using Pythagorean theorem. So the legs squared and added together, 7.7 squared plus 9.2 squared. Should equal the hypotenuse squared, so 12 squared. So you can see those are pretty darn close. They're not exact because these are rounded numbers, but that does check out. So those are my X, Y, and Z values. Okay, let's stop that video here.